We would now like to begin the third session titled Philosophy Behind the Creation of Programming Languages. Now please welcome Rakuten Institute of Technology's scientist, Mr. Satoshi Egi, and fellow of Rakuten Institute of Technology, Mr. Yukihiro Matsumoto.
Good morning. Okay, this is the two-phase session. So I'm gonna first talk about how to design a language. Then Egi-san will explain you about his new language, Egi-san. So this is the kind of curtain raiser for his talk. Okay, how to design a language. Okay, for most of us, even for programmer or non-programmer, the languages are given. So, for example, English is given. No one designed English language, or no Japanese. And for programming language as well, so we, except for James Gosling, so designed Java. So we just use Java, right? So, except for myself, so no other person designed Ruby. So I made a decision. I designed the language. But you, even you're a Ruby programmer or not, so you use Ruby, right? Or PHP or Python or any other language. So you are, in general, you are not a language designer. By the way, have you ever designed a language? The designing language is not really a difficult task. It's a kind of serious practice, but implementing world-use programming language is another story. But programming language is has kind of interesting attributes. Like it's unlike human languages, natural languages. They are intentionally designed. For example, the Ruby is designed to be an object-oriented programming language. So how many language designers you know? Like me for Ruby, Guido Van Rossum for Python, Larry Wall for Perl, and Rasmus Ledov for PHP, or James Gosling for Java, and Satoshi there for Egi-san, and you. I'm serious. So I encourage you to design your language, not in the sense you imagine, but so one day I met Dave Thomas. Well, we have several Dave Thomases in the computer science field, but this Dave Thomas. So he once said that programming is a process of designing your own DSL, domain-specific language. So in that sense, so your activity, the programming, the creating application itself is the process of designing your own domain-specific languages, right? So when you're designing or creating software, so designing the programming applications, so it's a process of designing your own languages. Because interface is fundamentally a language. So designing interface, designing APIs, designing frameworks, they are languages. So in that sense, even you don't create programming language like me, but you are designing languages. So we all design languages in the process of creating software, creating services, designing interface, creating user experiences. They are languages. So we have to be language designers, right? So we are language designers. So what is the key to design a language? That's the point. So the Larry Wall, who is the creator of Perl, with this face, beard. So he once said the 3 virtues of great programmer. So the 3 virtues of great programmers. So one is laziness, impatience, and hubris for virtues, right? So laziness, he meant the quality that makes you go to great effort to reduce overall energy expenditure. It makes you write labor-saving programs that other people will find yourself and document what you wrote, so you don't have to answer so many questions about it. That is laziness. Impatience, so the anger you feel when the computer is being lazy. So we can be lazy, but computers cannot. So this makes you write programs that don't just react to your needs, but actually anticipate them, or at least pretend to. So the smart computers. The hubris, the quality that makes you write and maintain programs that other people want to say bad things about. So these are three virtues of programmers. So we use computers to live better lives, right? So we utilize computers to serve for us. So we are masters of computers. So we have to make computers to understand our languages. I don't mean our language which is English nor Japanese, but it does not mean human language. So computer language that's designed for human in mind. So like say, for example, Ruby or PHP or something like that, or maybe user interface, that is the language between application and us users. So that kind of languages. So that kind of language should be designed human in mind. So the keys to design good interface or good language is several-fold. The first one is be concise. So the implicit is better than explicit in general if it is obvious. So the good principle of design in our community is one of them is the COC, convention over configuration. So if we can provide the reasonable default, so you don't have to specify every once again and again. So this is convention over configuration, so that you can reduce the time writing the configuration code again and again. For example, you don't have to write tens of thousands of lines of code like XML to configure your web services. So the second principle is DRY, which stands for the don't repeat yourself. So it's kind of avoiding duplications or avoid copying and paste. So duplication is bad, just because when you copy our code, so you copy the bugs as well. So that means if you find a bug here, so you have to fix those copied bugs all over. Or if you copy 10 the code everywhere in your applications, you may fix 9 out of 10, but leaving one will crash your application in front of the user. So that's bad. So the copying is very, very bad. So the good old days, like the programmer's effort was counted as the lines of number of lines you wrote for your applications. So in that days, so the copying is very good way. So only just click in, so you can double your effort. But these days, our effort is accomplished, measured by the value we provide for business. So in that sense, the copying bug is very, 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 very bad, right? So the copying is very bad. So the conciseness, code conciseness, is leads to productivity. Just because you have to spend less time in the code, the less code is more understandable. So our brain, the power of our brain is very limited. So the computers have no problem about the huge code. So it just execute. But our brain is very limited. So we cannot grasp all of your applications when your code grows into the thousands of lines of code or tens of thousands of lines of code or millions of lines of code. So in that sense, we have to abstract away in the detail so that we can forget about them. So we can focus on the very essence of the application. So the second one is avoid guessing game. The guessing game is the kind of trade-off between the conciseness and this kind of guessing. So you have to think to avoid guessing game when you design conciseness. The guessing game is so we have to sometimes, so the interface is very concise or dense, so we have to guess the user's or designer's intention. So that's pretty bad because you may fail to guess. So that is quite irritating. So my daughter, 11 years old, do some guessing game. So sometimes she says, so I want something good or something fun or something like that. So we parents proposed her to say toy or play or game or something like that, and she just says no. So we have to try again and again until we guess right. So that's so irritating for me. So I sometimes get mad at her. But the computers do similar things again and again if we design our language or our interface very badly. So we have to avoid that kind of feeling. So we want computers read our intention. We want computers read our intention. So we don't want to guess computers' intention or designers' intention. So we have to be very, very explicit. So because we are masters of computers, we are not the slaves of computers. But often we suffer alpha syndrome. Have you ever heard about the alpha syndrome? So when you play with your pet dog or pet cat or something, so they're cute, aren't they? So we hear them, so we do very good things to them. So sometimes those pets, those animals, do misunderstand that it is a leader of the group, leader of a family. So they became more and more selfish, more and more violence sometimes. That is alpha syndrome. The similar things easily happen in the relationship between the computers and the humans. So we stand that kind of guessing game toward the applications, the computers. So the computers becomes our masters in psychological effect. So that is quite bad. So we don't have to stand that kind of the guessing game. So similar to that, the mind of psychology. So our feeling matters. So our activity, the programmer's activity, are more often misunderstood. So the people out of our business thinks that our activity, programmer's activities, are something between computers, something toward computers. So we have to deal with machines. But in reality, so the most of the time we spend is to find out how users feel. The users are human. you as a human being, so we care about human. We deal with human psychology, human mind. So we have to spend most of our time toward human mind. So in that sense, our feeling matters very, very much in designing our languages or our interface. So including consciousness is one of the psychological effect, or that kind of the alpha syndrome I explained previously. So small limitations toward using computers during using the computers stacks up. So be sensitive to that kind of irritation. So be sensitive. So you have to be very, very impatient about those kind of irritations. Be impatient. So no one's perfect, so we all fail in design or creating software. But that indicates the design is hard, very, very hard. But we can try again. So try again and again to create better language, better interface, better interaction between computers, and so to satisfy users' feeling, so to avoid users' irritation. So never, never give up until you success. So the fourth, the key to the design better language or better interface is guide your users. So we want freedom in general. So freedom is very good things in general. So freedom. But the absolute freedom is kind of scary. So we have to decide what we do without any clue. Or we can lost in the desert of reality of freedom. So the absolute freedom is very, very scary. So we provide some kind of convention or guide or model or basic policy. For example, the object-oriented programming itself is a kind of the mind model during the programming. So you can create objects, stack up the object to create your application, right? So, or functional programming is also the model, the mind model of creating software. So we can provide that kind of model or mindset or illusion to guide users to create his own software, or create users to guide the task they have to do. So sometimes in the context of the user interface, we say affordance. So the vague guide toward the users interact with computers, affordance. So in the sense of programming, pattern matching or any other mind model can be provided, or you guide the graphical user interface sense, the button and the menus are kind of affordance. So this kind of mind model is pretty much important to guide your users. So be nice to users. So because interface is fundamentally a language, right? So we have to prepare good language or good interface to guide your users. So the designing good language, the choosing good interface, it can increase productivity of your users. So mind your language designers. So consider yourself as language designers hereafter. So you haven't consider yourself as a language designer before, but in that sense, so creating software itself is a designing languages. So you are language designers, design great language, design great software and interface. So that you can create great software, great services, and change your world. Thank you. now your turn. So, please, Egi-san.
Thank you. Okay. Thank you for mentioning me, Matsumoto-san. Today, I'll make a presentation on the thought behind the creation of Edison. At first, let me introduce myself. I am a researcher in Rakuten Institute of Technology. My research interests include programming language theory. Here is my brief personal history. I released the Edison programming language in 2011, when I was a student of the University of Tokyo. I have continued the development of Edison even after I graduated the university in 2012. And I joined Rakuten in 2013. After that, Edison is gradually getting popular. And recently, I have received several awards for creating Edison. And today, thankfully, I am giving a presentation with Matt. Edison has been released as open source software, and its website. Please visit it when you have time. Today, I'd like to talk three things. First, the importance of representation in science. And this is the reason why I am researching on programming language. Second, the process of inventing a new representation. Finally, I will introduce Edison and talk how Edison invented. At first, let me talk about the importance of representation in science. Humans have invented various representations up to the present. Here are examples from number notation, mathematical expressions, chemical formulas, and programming language. The representation has been developed over a long time, and various number notations are developed in each cultural regions. Roman numerals, Chinese numerals, Hindu-Arabic numerals are in this list. There are distinct differences among the readability of these numerals. This difference is not because we are accustomed to Hindu-Arabic numerals, but it arises from the mathematical features that each numeral is based on. Let me explain this difference further. The difference becomes bigger when calculated using them. It's harder to calculate multiplication using Roman numerals and Chinese numerals. And this is a diagram to show the role of representation in this research of science. First, we observe nature, and it develops our intuition. Intuition means chokkan in Japanese. This process helps us to develop better understanding, which leads to better representation. And good representation helps us to deepen our understanding of nature. For example, in the Middle Ages, after Hindu-Arabic numerals were introduced in Europe, European mathematics developed significantly. We can see that in the history of mathematical symbols too. The next topic is process of inventing a new representation. The process of inventing a new representation can be divided into three phases. In the first phase, we study the features of nature and develop our intuition. But then we realize that there is a gap created between our intuition and the existing representation. In the second phase, we research in order to find the reason for the gap. In the third phase, we implement the result of research and create a new representation. Let's see the process in more detail with the example from number notation. In the first phase, we study the features of nature and develop our intuition. In this phase, the notion of number addition, multiplication, and various theorems on number are discovered. These discoveries include the feature that all numbers are uniquely represented in the form like this. In the second phase, we analyze the gap between our intuition and the existing representation. In this phase, it is discovered that the feature on numbers explained in the previous slide is useful to improve the number notation. There would be many researchers who discovered such features on numbers, but there are only few researchers who can discover that it is useful to improve, this feature is useful to improve number notation. It is very difficult to notice this connection before the positional notation is invented. In the third phase, we design new representation utilizing the feature found in the second phase. In this phase, positional notation was invented. Developing the whole system was really difficult. In these three phases, we invent a new representation. And finally, I'd like to explain about the Edison programming language that I've created. I found a new abstraction for new representation in programming language and implemented it in Edison. Please take a look at this mind map on the theory of programming languages. There are two kinds of abstractions. The abstraction of algorithms and the abstraction of computers. The abstraction of algorithm contains three topics: function modularity, type system, and pattern matching. Edison improved the pattern matching part. Edison focuses on the fact that some data types, such as collections, are treated as various data types in the programs. For example, a collection of cards is sometimes treated as a list of cards, and sometimes treated as a multi-set of cards. When we count or sort them, we treat them as a list. But when we find an identical element or element in sequence, it is natural to treat them as a multi-set. There are mainly three kinds of patterns for collection: nil, cons, and join patterns. We combine them to make various patterns of the collections. Nil patterns are a pattern that matches with a collection with more than one element, and divided it into the head element and the rest collection. Join patterns are a pattern that matches with any collection and divide it into two collections, the head part and the rest. In this definition, cons and join patterns are applicable only to lists and not applicable to multi-set and sets. So we can't treat multi-set and sets directly. Edison generalized the meaning of these patterns and makes them applicable to others. Edison generalized the scope of patterns from head to any. Cons patterns divide a collection into an element and the rest, not the head and the rest. Join patterns divide a collection into just two collections. We don't care orders of elements. When target is a collection 1, 2, 3 and treated it as a list, a constant pattern divides it into 1 and 2, 3 as the previous slide when we treat them as a list. But when we treat it as a multi-set, we ignore the order of the element. So a cons pattern divide it into 1 and 2, 3, 2 and 1, 3, and 3 and 1, 2. When the target is treated as a set, we ignore both of order and duplicates of the elements. So a cons pattern divides it into 1 and 1, 2, 3, 2 and 1, 2, 3, 3 and 1, 2, 3. Here are pattern matching expression in Edison. Please note that Edison pattern matching expressions take a matcher to specify how the target is pattern matched. If we set a matcher list integer as the first sample, the target collection 1, 2, 3 is pattern matched as a list of integers. If we set a matcher match set integer as the second sample, the target collection is pattern matched as a match set of integers. This matcher is one of the unique inventions of Edison. The expressive power of Edison pattern matching is so strong that we can express poker hands pattern matching in a single expression like this. All poker hands are expressed in a single pattern. Here is a pattern for straight flush. This means all cards have the same suit. And this means numbers are in sequence. Edison supports a pattern called a nonlinear pattern. It allows us to refer the value of the variable whose values are bound within the pattern. A pattern that begins with comma is called a value pattern. A value pattern matches with the object equal to the evaluated value of the expression after comma is after comma. Here is a pattern for two pair. This means the suit of the card is not important. This part means we have two pairs of cards that have same numbers. We can create patterns even for Mahjong. This program determines whether a Mahjong hand is complete or not. We can write that in one slide. In other languages, it will be at least 5 times longer. This is a more realistic sample. This program solves the traveling salesman problem. In the Edison system, we can match patterns of various data types. We can create patterns for graphs as well, like this. Currently, I am working to solve real problems in Edison. There are several possibilities to do that. First, I'd like to mention that Edison can represent complex tasks for daily work in a simple way. Second, there is a possibility that Edison is useful to financial problems by describing complex patterns accurately for chart analysis. Third, Edison provides a way to pattern match for various data types in a unified way. So it can be useful for data query. Fourth, pattern matching in Edison can be paralleled automatically. So we can write parallel programs very easily in Edison. My next year goal is to utilize Edison in one of these fields. Finally, let me talk about the next version of Edison, Edison version 4. Edison version 4 will aim to become a popular language. For that, I will focus to improve usability of Edison and seriously proceed research on friendly syntax. We will provide completely new syntax in the next version. We remove at least this many appearances. I hope you'll enjoy it. Here are links for further information on Edison. I have already uploaded my presentation on my website. Please check it. Finally, Rakuten Institute of Technology is hiring researchers, data scientists, coordinator, and part-time research assistant please contact us if you are interested in these posts. Thank you so much for your attention.
Yeah, if you guys question for me or Egi-san, so please raise your hand. Could you hand mic? Yeah.
Thank you for the presentation. I have a question about Edison, and it seems like it is similar to Lisp. Did you make Edison from Lisp?
Yes, I refer the syntax of Lisp to design Edison, and it is currently implemented in Haskell, using Haskell.
Using Haskell. そうですか。なんか文法がI think syntax is なんだ similar to Lisp, so yeah. So I'm familiar with Lisp, so it is not difficult to program, but for other people, I don't think so. So I think that is the problem of the Edison, I think.
I improve this part in the next version.
Yeah, thank you.
Hello. Actually, I didn't study Edison much, but so far I found it is like more functional oriented. I mean, very pure. It's very good feature definitely, but sometimes it is a bit difficult for programmers to program too much pure functional way. So I just feel like if it is a bit more about operator oriented. That means just an example like cons in Haskell or OCaml. There is very easy way, like x colon and then like xs.
Yes.
But here, yeah, it's writing like cons and then x and then xs like this. So did you think about it like making it a bit more operator oriented? Yeah, that's my question.
Yeah. Yes. Thank you. I'm considering that. I am considering that.
Okay, actually, I am very interested to work with you anyway. Maybe I'll talk to you later.
Yes. Thank you.
Yeah, we have 7 more minutes. So either you, okay, another question?
Okay, I have a different question. So nowadays, program verification, I mean in a formal verification, it is getting popular, especially after separation logic invented and some success of Facebook's Infer system. And there are a couple of languages are also enriched with assertions. I mean, in programming language, programmers can write assertions so that on the execution time, before execution time, it can be actually verified whether the block or a function can be, is perfect. So I'm asking, like in Edison, do you have any plan to include this? And also Ruby, I'm also asking. Yeah, this is kinds of new life, new feature.
So program verification を検証するようなことをエジソンに入れる考えはありますか?
Yes.
Yes.
I'll in my plan in future I'll implement static type system in Edison and improve verification more.
Okay, thank you.
Yeah, the type system is kind of the program verification. So the the revealed program verification represented by something like the COQ is too difficult to apply the huge application or everyday application. So that in that sense, I have no plan to apply that kind of concept in the real world programming language like Ruby. But I have a vague plan to apply on the future version of Ruby into some kind of the partial static typing through the kind of global type inference. So in that sense, we have introduced some kind of the program verification, compile time program verification. And also we have several Ruby gems, Ruby libraries to accomplish the design by contract, which is kind of the runtime verification. Yes. Sorry. Next.
So A-4 math about Ruby. So if you for the new version of Ruby, we see you make some research about new syntax, like you create stream, new language like kind of strip, and I would like to know what will be like the new Ruby 3.
The Ruby 3 talk will take more than 3 minutes. But I have several ideas to implement concurrency into the new version of Ruby 3. But we are not going to change the syntax. But we might have several additions to the language in semantics. For example, adding several the concurrent operators or something like that. But that would be small. So that the future Ruby would not break compatibility.
Could you give some real-world examples of Egisan and how it's being used at Rakuten, or if it's being used internally?
Currently, in Rakuten, just I am just me. And I am currently searching real big application, real problem.
Could it be used for parsing like web pages? That's kind of a form of pattern matching.
Yes.
Yeah.
Yeah, the other day we talked together about the application of Egisan programming language. So for example, like the web crawling, so you can match the web pages match the pattern, so that kind of determination can be done quickly in Egisan programming language, for example. So I think we have that kind of real world application for Egisan, so that we have to work on.
So I work at Slice, and we parse emails to extract information from emails.
For example, that kind
so we might explore using Egisan for something like that.
Thank you. Let's work together.
Yeah, let's do it.
Thank you very much. And I love to use Ruby to implement prototyping my ideas. And on the other hand, we use documentation like UML to communicate with other engineers to develop a large system or something. And you mentioned that the interface, to define interface is also the programming. And I'd like to have you comment on the UML or documentation covers programming, or the programming covers the documentation.
Yeah, that kind of problem or that kind of choice of the design tool is highly dependent on the background of teams. So if your team is familiar with the Ruby syntax, you don't have to create any UML. So they just communicate in Ruby. But if your team is the multi-language team, so some people are very good at Java, or some people are good at Ruby, so they are separated in the technical way. So they might need to introduce that kind of common language. For example, the UML. So it's highly dependent to your team configuration or something.
How about in Rakuten?
Yeah, but the team is Rakuten is not the uniform way. So the member in the RIT is different from the DU. So the team member in the DU is different in the level of understanding or the preference of the language. So you have to choose your own tool for your own project.
And I expect the language will cover the documentation. We don't need to documentation.
Yeah. So if your team is highly uniformed, so the communicating directly in your programming language is much more efficient and productive. So in that case, I don't recommend UML, but otherwise, so UML might be a good choice.
Thank you very much.
The lady back there.
I really enjoyed you talking about how you needed to have hubris to design a programming language, but also spoke quite a bit around sort of the need to listen to your users and be really empathetic. So moving forwards, how do you balance that kind of hubris with user empathy to continue to develop and continue to refine on feedback?
Yeah, that three virtues indicates that we can okay to mad at programming. So, during your programming activities, but in contrast, so you have to keep your anger inside your mind. So don't publicize that. So don't mad at your team members, don't mad at your clients, but keep your anger toward the bad design or bad result in your mind only. So that is my balance.
Okay, I'm afraid we're running out of time, so we'd like to end this session. Thank you very much, Mr. Egi and Mr. Matsumoto. Thank you.